Let me start. Welcome everyone to this tech talk section. I'm Daehyeok Kim. I'm a senior researcher at Microsoft. So we've been using P4 language to express custom data plane logics for many different hardware and software backends, including hardware and software switches and network interface cards. So in this talk, Jamal Salim, who is the CEO of Mojatatu Networks, will be talking about how to leverage P4 for the traffic control or TC subsystem in Linux. Jamal, the floor is yours.
Thank you. As Daehyeok said, my name is Jamal Hadi Salim. On behalf of my co-authors, I'm presenting our ongoing work, getting P4 over TC. We currently refer to this project as P4TC. As you all know, the most difficult thing in coding is coming up with names. We initially named this project TCP4, but it was getting confused with some new version of TCP congestion control. This talk is an abridged version. It's very condensed. Please show up at our meetings, for which I'll provide information at the end. Details will be on the last slide. So what is the overall goal of P4TC? It's to facilitate taking a P4 program and running it in the Linux kernel data path, while also being able to offload the same P4 program if required. As mentioned earlier, a core requirement of P4TC is to be able to offload a P4 program using the Linux kernel infrastructure, and in particular, the TC subsystem. Coupled to that requirement is ability to script the Linux kernel data path using a P4 program. I'll detail a little bit more what that means in the slides that follow, because it could be a little confusing on the outset. From an ecosystem perspective, we want to attract two types of personas. The first one is the P4 developer. The focus of that persona is on writing the P4 program, making sure it works. We hope to make P4TC usable for anyone who's sufficiently familiar with P4, but not necessarily with the Linux kernel. The second persona is the Linux ops. This is your classical sysadmin type person. This is a much, much larger population that's present in the Linux world. So we want to take advantage of that community. They're not necessarily developers in the classical sense, but they can script away at things. We are going to support some features that are slightly outside the scope of P4 at the moment, which means these are things that you can't describe using the P4 language. And for those outliers, we're going to allow scripting. With that being said, the P4TC solution will go beyond P4 in the focus for network programmability. We hope that we can grow the network programmability world by marrying both Linux and P4, and that some of that experience can be brought back into P4 over time. So the big question is, why put this in the kernel? And the simple answer is the end goal is to transcend P4 into ubiquity. So let me explain that, maybe with a rhetorical answer. The Linux kernel data path has a massive reach into the technology infrastructure landscape, whether it's cloud, enterprise, data centers, etc. Whether it's a resource management infrastructures like containers with Kubernetes, VMs with OpenStack, middle boxes, not forgetting to a very large extent, the number of developers, operators, academic, tinkerers, etc. that are omnipresent on the Linux kernel. We want to be part of that. We picked the TC infrastructure because it already maps very well into the P4 match action table approach. And it already today offers offload infrastructure using device drivers. The P4TC design makes very little change to the kernel code, but adds new code that is specific to P4, which can be turned off if you have no interest in P4. There are several approaches that have been taken today that embed P4 into the control data path that sits in user space stacks. A lot of them are centered around DPDK in order to, with an end goal of improving performance. We argue that achieving ubiquity is more important than network in the network programmability world than the sole focus of performance. And if you really want performance, hardware offload is becoming very common now, and you can go that path. There's a cost in usability and ubiquity. Granted, some of the motivation from some of the folks that have been using DPDK is to try and totally bypass the kernel upstream process when they want to introduce new data paths. I believe we're going to alleviate that problem here with this approach that we call scriptability. The next question that pops up is why you're not using eBPF. As stated earlier, our hardware offload is a key requirement, which eBPF on its own in the kernel doesn't provide us, but TC does. Note that eBPF, we're not arguing against eBPF. It has a lot of value in tooling small programs at different points in the kernel. But if you have ever, as we have, tried to write complex programs, and I think Turing completeness in this case, with eBPF, we run into a lot of challenges because it's still evolving. The more complex program you write, the more you'll have to deal with the quirks in the verifier, in the compilers, in the APIs, in the version of the kernel you're using, etc. And as stated earlier, one of our goals is to, or I would say the largest personas we're targeting, the scripting ops persona are not interested in coding, neither in P4 nor in eBPF. Okay, so next I'm going to go into some of the motivation that got us where we are. So if you want to put things in the kernel and you want to do offload, a key upstream requirement is that any network feature that is to be offloaded must have a software twin in software, basically, that is functionally equivalent to what's in hardware. In other words, as the diagram shows here, given same input to software as in hardware, we get the same output in software as we do in hardware at a relatively lower data path performance. What this means is you can run P4 programs in absence of hardware offload, and likewise, you can offload everything without any software packet processing. In addition, TC allows you to split some of these offloads. Some could sit in the software kernel, some could sit in hardware. So for example, you could take a table in a pipeline and put it in hardware or in software, and the rest sit in hardware or software. Or you could, within the pipeline, you could take a bunch of entries and put some in hardware and some in software. What this means, you can also do clever splitting of hardware versus software processing. There are benefits to this. This feature essentially provides you ability to run in VMs, containers, bare metal, meaning that P4 can be used now in other environments where it was not envisioned. Example, think of a scenario where you have Kubernetes pure software deployment. So coming to the core design principle, which is scriptability. Scriptability framework is used in P4, is driven by a templating architecture, which I'll describe in coming slides. But what do I mean by that? I mean that a P4 program is prescribed as a template set of scripts in the control plane and installed into the kernel as policy. You can see, what you can see on the diagram on the right-hand side there is I write scripts in the kernel. The kernel mechanism takes these scripts, installs them in the kernel, and then subsequent to that, I can do runtime updates of tables, etc., and I can target hardware or software. This means that there is no need for a kernel change just because I wrote some P4 program, as it is today, for example, in this world of TC Flower. In other words, there is both kernel and user space or control space independence. I should note that there's already prior art to this. We did not originally came up with this idea. There's a classifier called U32 that is totally scriptable from user space. There's a packet editor called pedit. There's a metadata edit called skbedit. So the motivation for kernel independence is driven by many reasons, mostly to do with cost and time factors. Let's start with the time and people resource investment. A cost factor in dealing with apps. If you want to deal with upstream, you need to hire people with special skills, both social and technical, which is not cheap. Time factor, it takes 1 to 4 years to upstream a kernel feature before it shows up on your enterprise for a supportable distro like Red Hat 9.2, for example. There's a cost factor. Of course, you can go to Red Hat and say, I want to speed this up because we have this 3-line kernel change we made that it adds a feature that we want, and you pay NRE fees. Okay, that's a cost. And there is still a timeliness involvement here. Distros tend to be 6-month period distro release cycles. There is also cultural factors that we have seen, or process factors that we've come around across. One of them is we've seen in some data centers, in particular telcos, that don't like to add new features. So if you wanted to change that proverbial 2-line in the kernel to enable something, they, just like with the distros, they have to go through their process of enabling that feature. So as a matter of fact, they're slightly more complicated because they just don't like things that get compiled into binaries. You can't just load any binary you want in there. It has to go through the 6 months, 1-year vetting process as well. However, if you have a kernel feature and all you needed to do was to enable a script, then they would allow that just fine. So scriptability essentially helps us accelerate this kind of feature velocity while saving costs as well. Now, say the side benefits to this is lowering entry point for any new defined data path or protocol. The lesser code we submit upstream, the better it is for kernel maintenance overhead. The fact that there is no need for you to battle any new kernels, compilers, tools, you don't need a lot of gurus in-house, is very beneficial. So where are we going with this? We are going to, once the feature is completed, we are going to upstream it into the Linux kernel, into the IP Route 2 utility set. And subsequent to that, anything will be just bug fixes, and any bugs will always exist. But there should be absolutely no need to update any kernel or user space in the commons case. And so we hope that this will this is what we wish for, and this is our plan, and we'll see what happens. Having said that, there's also the general design goals which we're encompassing into P4TC. We have desire to be P4 architecture independent, so we would like to support both PSA and PNA and maybe some other architectures instead of being, because Linux runs on both switches and NICs and hosts basically. We want to support multi-vendor implementations of P4 hardware. We want to enable debuggability to make it easy to debug for both developers and operators. We're striving to do admission control for hardware resources at the boundary of control and data path. There may be some scenarios where that doesn't quite work, but we're going to do that on a better than best effort. One of our goals as well is to have a very efficient control plane table CRUD messaging, so that we can have very low latency for an individual transaction to do a table update, or very high throughput for a batch of such transactions. So let me jump into the workflow, how someone will create a P4 program and then proceed to runtime control it. So the first thing is, if you look at the left corner, the left side, it shows the process. What you're seeing is the standard way of doing this in P4 is you write your P4 program, you feed it to a compiler, it outputs vendor hardware specific binaries, you load those into your hardware, and now you have a new data path running in the hardware. The other option is we're going to add an option to generate the TC templates at runtime. You basically provide an option. That option creates a backend template set of scripts. There's 4 scripts. There's one for a parser, one for metadata that's maybe defined in the P4 program. If there's no metadata, then nothing gets generated in that case. There's one that describes the pipeline of how the tables are connected and what the logic is in the P4 apply control block. And if you have new actions that are not supported at the moment in the kernel, because TC actions do exist, and there has very good mapping between what is supported in hardware versus a lot of the standard actions in P4. If you don't have any of those, then yeah, we generate those as well. So in the case, so that's how someone writing P4 code will proceed. I spoke earlier on about possibility of a Linux sysop person that would manually create these templates that you see in green, load them into the kernel, and basically exercise that the equivalent of a P4 program. And we're looking at tooling where we can suck this out of the kernel and actually reverse generate a P4 program. Initially, this idea was for debugging to make sure that whatever is put in the kernel can be backward generated into a P4 program. But it could be useful for the second persona I described earlier. We also envision a possibility of vendors either shipping a P4 that today in Linux have NICs to which they can't expose all the features they have because of the APIs available in the kernel, that shipping a P4 program which can then be compiled and loaded into the kernel will help expose more features than they do today. I'm going to jump to, so that was how you would install your program. Once you install your program, you then instantiate it in the kernel. What you can see on the left-hand side is the command to load, to instantiate, to create an instance of the P4 program that's at the top, which has 4 tables. What you can see is this program, called myprog in this case, is loaded at the ingress of a device called eth0 with a classifier, which we're writing, called the P4 classifier. And it describes the sequence of tables that are going to be exercised for this pipeline. Now, the tables are described so that we can specify a key ID. Keys are given IDs, and this is pretty standard in P4. But in our case, we allow more than one key. Like I said, these are some of the features that don't exist in P4. One or more keys that can be used for the table lookup. And the idea here is, in order for us to do scriptability in a reasonable way, the templates will have the key ID definitions, but the data path will just be told what to use. It just makes it easy. PNA has a conditional structure where you can select maybe source IP in one direction for a key and then destination IP in the other direction. In our case, this is statically defined. On the right-hand side, you see now once you've loaded your runtime pipeline instance, is you start updating the tables of choice. So in this case, this command is shown is updating table number 4, and the keyword skip software implies that I want this to be offloaded in hardware. There are 2 keywords. One is called skip software. The other one is called skip hardware. If I say skip hardware, I'm actually loading this table entry into the instance of the table that sits in software. I'm going to go into a little bit more details on both of these. Number 1 is the filter, which is a pipeline instance. As you can see, there are 2 bubbles. One sits in software in the kernel on the left-hand side, and the other one sits in hardware. They're, like I said earlier, they're functionally equivalent. So once you load it, this is, well, might as well be statically defined because that's how P4 works. So for each program, I will have a pipeline of tables as such. When you instantiate the program on the first using a TC filter, you basically just define the keys. So, and you can have multiple instances of this program, maybe on an ingress of one or more ports, and then on an egress of another set of ports. The important one, that the most frequent activity that will happen is table updates. What you're seeing here is a human operator or a control plane will type in commands to update the table entry. They may or may not specify skip hardware or skip software. If they do specify skip software, it goes on the table instance that sits on the that you see labeled as skip software on the left-hand side of the screen. And if they say skip, if they say skip hardware, if they say skip software, it goes all the way down and the driver loads it into the appropriate hardware table. I mentioned earlier that we're going to be rejecting any entries that exceed capacity that's known, and the capacity will be known ahead of time after the compilation via the templates. This is the best effort. If the hardware is self changing and is adding more table entries on its own, then that would be a best effort basis. But in general, we should be able to restrict if the P4 program is saying only 8K entries can be added to this table, then at 8K plus 1, we can tell the control plane the table is full. On the left-hand side of that, you see this introspection path, and that is for discovering. We're not going to write user space software either, but we can introspect a P4 generated info file and watch and resolve names and keys and sizes through that detail. Don't have much time to go over those details. I'm going to jump quickly to a bunch of objects that we introduced into the kernel. There are several objects in this presentation. I'll discuss a couple of them. One is how a table will look like in the kernel, and the other one is how a pipeline will look like and how templates play a role in all this. So if we look at tables, what you can see is there are two hooks that are derived by looking at the template. The first one we call the table pre-action hook. Any activity that's required to occur before a table lookup happens at this stage. Like I said, this is derived from the template. The template predefines essentially actions that execute at this stage. For example, the most common action here will be we're going to invoke the parser and or metadata bus and retrieve elements that then are used to construct a key. The second template on the right-hand side, which you call the table post actions, is typically would run a set of actions, but the most prominent one is if there was a second table, it would be used to branch to and apply the next appropriate table. The middle part is the lookup phase, which is an equivalent to an algorithmic TCAM approach, where a list of masks per table may be linearly iterated, and the best match is then used, disambiguated using some priority scheme. For lack of time, I won't go into the details of that. Next, let me jump into the pipeline pre and post actions. So again, these are generated by the compiler. The templates are generated by the compiler. When I instantiate the TCP4 filter, they're resolved, and that TCP4 filter will have instances of actions that sit on both the pipeline instance pre-action and the pipeline post actions. A pre-action hook is executed before any table activity occurs in the pipeline, and a post-action hook is executed at the end of all table activity. The combination of the table and pipeline pre and post actions are essentially the scripting of the P4 apply block. Maybe I'll show a simple example of a program of how this would apply. Here's a table, here's a pipeline that has two tables. We go from table 1 to table 2 from a control block. If there was a hit, and if there was a miss, we would go to, we'll terminate the pipeline, essentially, jump to the pipeline post actions. And here is a slightly more complex program, which has 4 tables. The first table, my table 1 inst, can branch to one of 3 tables. In the middle 2 tables can branch to can only go to the last table. So during all this exercise, we did run into gaps, the kernel gaps, for example, actions. The TC actions do not define the concept of action selectors. We're adding that in the kernel. The idea of extents is a bit tricky because there's possibility of extents not being seen by the data path if they're proprietary. We are undecided on what to do with that, but for anything that can be expressed using P4, we're very likely going to generate that code. By that code, I mean we're generating a bunch of actions that will take care of it. Come to our meetings for more details. From a P4 perspective, I described the concept of multiple keys. The concept, there's other things, such as we want to create multiple pipeline instances or multiple table instances. This has a lot of pragmatic need in the software world, and we're hoping that we should be able to transfer that requirement into the P4 hardware. It's a bit tricky to do it in P4 hardware, but we hope that the hardware guys will evolve to meet our needs. There are other small things like, deparser behavior. In software, you are not doing a sort of parallel pipeline execution. You're doing things linearly. So the current TCP behavior is we do inline editing of packets. So if I have a packet that, if I have actions that say mirror to port 1, then change the destination address, then mirror to port 2, you don't wait for the deparse at the end to edit the packet, because what will happen then is both, in some hardware, at least what we've seen, is both ports now see an edited version of that packet. It could be a bug in the hardware, but it's perceived to be, so it's perceived that's how the hardware deparsing works. So we are looking at doing inline editing when necessary. And with that, I'd like to say thank you. Our project status, like I said, is coding is still in progress. We have a mailing list to subscribe. I'm going to leave that on the screen. Just send an email called subscribe to that list. You get notified of our meetings where they'll happen. The project is still incubating. Only serious contributors are welcome at this stage until we start passing packets, which we hope is in about 6 months. And I have a bunch of backup slides you can read afterwards, how we model the TCAM into our algorithmic approach, which we call a pseudo TCAM. And I'm going to end it there. Thank you.
Great. Thanks for sharing the great idea. I think P4TC is very interesting approach that could be potentially could be applicable for various use cases. So my first question is like, what was the main technical challenge you faced while you are developing this framework of P4TC?
So for the record, we're still developing, but you know, the challenge is a lot of the kernel process or upstreaming process is you add features as needed. And that means, let's say I want to add parsing of a new header or a classification of a new header. I have to go and change the kernel code for parsing. I have to change the kernel code for classification. And then I have to change the control plane to understand how to configure these things. And our motivation for this is we don't want to do any of that, right? We want to have enough architecture in the kernel that would allow us to just send just a new CRUD command and it should just work. Load the template as needed without making any kernel changes. That has been our biggest change, and I think probably our biggest architectural contribution.
Makes sense. And if I understand correctly, the capability of TC subsystem is pretty simple and somewhat limited, especially compared to alternatives like eBPF or DPDK you mentioned. So given this constraint, our capability, what are the key use cases enabled by P4TC? Sorry. Yeah, could you give me some examples?
I wouldn't classify it as something simple. I mean, it does a little bit more than what P4 exposes in the sense of match action tables and flexibility in that space. That and I would say that P4 is, because the limitations are because the constraints are in hardware. eBPF is not the same thing because number one, eBPF can't meet our requirements because it requires compilation. I described the reasons why we don't want that. DPDK is running totally in user space, which bypasses the whole kernel ecosystem. Now, the DPDK folks do that for a reason, which they say is performance. Our angle, our counter argument to that is, if you want performance, you get some hardware offload. That the fact that I can write a script, therefore lowering the entry point, I don't have to go and write some complex DPDK and fight with how I would do the PCI transactions or how I do I/O. If I can do this in, in the kernel, then that is more important in terms of spreading the ecosystem than anything DPDK can offer me from that perspective. Right. And TC already had, I don't know if you're aware of this, but you can do offloads today with TC into specific hardware that can support P4-like architecture. Has been doing it before P4 came into play, basically.
I see. Yeah, that makes sense. And regarding the offloading part, hardware offload part, so would it be possible to partially offload a P4 program to the hardware? And if so, should developers need to specify which part of this P4 program to be offloaded, or will the compiler do this automatically?
It's the control plane that does it. But yes, the answer is yes. You can either take a part of the pipeline and put it in hardware, depending on which direction you're going. Are you coming to the host? Then maybe a bunch of tables of the initial tables will be in hardware, and then the final tables in software. The alternative is you can have the same pipelines in both software and hardware, and only offload parts of the tables into hardware, right? Who decides this? It's the operator, the person who deploys the program, as opposed to the person who wrote the program. And I'm sure it'll be based on some hardware constraints. Hardware can't do 1 million entries. You may have to split the software in a certain way and then keep refreshing the hardware tables as needed.
So the developer can put some annotation on the P4 code to specify which part of the code.
No. It's after you've written your program, you write it as if it's going to run in hardware. Then the splitting is done by the controller. Whoever, or a command line, the administrator basically does that.
I see.
The assumption is that the P4 program is not targeted to some hardware only, right? It's targeted to a multitude of P4 data path implementations in hardware, and some may have different capacities, right? If I have only 8K in one table, but some other hardware has 1 million entries, I would have to put the 1 million minus 8K in software probably, and then do some sort of eviction algorithms that will replace what's in hardware. Your mileage may vary, but that's the power that's provided to you.
I see. Makes sense. Right. And in the workflow diagram, I saw there's a vendor-specific backend compiler in the figure. So is that a part of P4 TC framework, or does some hardware vendor should provide it?
So you're talking about in this figure.
Vendor hardware backend.
Oh yeah, I think that would be hardware provided by the vendor.
Hardware, I see.
But not that on the right hand side, the grayscale box that is that could run. I don't need hardware to be running a P4 program. Right. But if I could generate it and generate an equivalent hardware targeted binary, then and the two are equivalent, then yeah, I could start telling the control plane to offload to that hardware. In other words, those two will be matching, right?
Yep. Makes sense. And one last question is, what's the next step for your project, for this project?
We are coding right now. We hope that around end of October, we will have something to share with the rest of the world. And that we're welcoming contributors, but you have to be serious, right? You can just show up there to just critique, show there and work. That's what we welcome right now. And there's a mailing list. Anybody, that is a discussion mailing list. Anybody can join. There's a development which is just restricted to only people who are contributing. But this is a multi-vendor. It's not intended for any vendor. It's an open source project that is intended to benefit the P4 community, regardless of the vendor.
Okay, thanks for your kind answer. Yeah, that's pretty much it. Thanks again for your great presentation.
Thanks.